So welcome to the post-class video on integrated rate laws, how concentration varies as a function of time.
Okay.
And so as we found in class, these are the equations that characterize for zero order concentration equals negative kT plus the concentration at time 0. So remember these subscripts at time t and 0. Right? So for first order, the easiest way to look at it is if you take the natural log of concentration equals negative kT plus natural log of A0, and then for second order, 1 over AT equals kT plus 1 over A0.
And will they need to memorize these equations?
Pretty much you need to memorize these. In my class, you get to have a little note card, and so that's an important thing that you'd want on that card.
Okay.
But what's more important, what you need to know is how do you use them? And so one way that you use them is if you're given a problem of time and concentrations, just pick the right one, plug in the numbers, and solve for an unknown. And I'll do a problem at the end of this, kind of like that. But the other way is if you're given concentration versus time, how do you use that to determine the order for the reaction? And the way that you do that is you ask the question, well, these are three different equations, and they're all in the form of a straight line equation. This is concentration versus time, gives you a straight line. This one, natural log of concentration versus time, gives you a straight line. And this one, 1 over the concentration versus time, gives you a straight line. And so you have to ask the question, which one fits the straight line? You have to plot all three, which is a little, little work, but not that bad. Only one of these will give you a straight line. The one that matches tells you what order it is. Okay? And then the third objective was about half-life. How long does it take the concentration reaction to drop in half? And what we found by just looking at the data was that for a first order reaction, the half-life was constant half-life. For zero order, the half-lives got shorter and shorter. And for second order, they got longer and longer. Right? So that's another way that you can kind of figure out what the order is. The equation that's maybe most important there is that for a first order reaction, the half-life, the time for that, equals natural log of 2 over k. So if you know half-life, you can figure out the rate constant. If you know the rate constant, you can figure out the half-life. Okay, so this activity was a little bit long, and so we didn't get to finish that last objective completely. And that objective was about using these equations. Right? So I just want to do one of those examples. And so here's the problem from the activity, and hopefully you've already done this. If you have, this is a double check. If you haven't, we'll work through it. So in a particular solution, hydrogen peroxide decays with first order kinetics by the following reaction. 2H2O2 goes to 2H2O plus O2. The half-life of the reaction is 10.9 hours. If 1 liter of solution initially contains H2O2, concentration of 1.5 molar, what will be the concentration after 24 hours? So I know I'm going to have to use integrated rate laws because I'm trying to predict the future. What is it going to happen in 24 hours? Exactly. So what do we have to do here? This is actually a couple steps. So I know I'm going to have to use this first order rate equation. A few of the other things in here, I know that my time is going to be 24 hours. That's the time that I want to know about. So that's going to go in there. This concentration at 0, what's that going to be?
We know that, here. There's the initial concentration. I was looking for it, I wasn't sure. 1.5 molar.
Right, so 1.5 molar, that's going to be our concentration.
At time 0.
At time 0.
Right, but we want to know what it's going to be at 24 hours.
24 hours. So that's those things. Here's my unknown. I want to know the concentration then.
Right.
The only other thing I need is this K.
Right, and it's a rate constant. So
rate
it's
constant.
like, where are we going to get that from?
Where are we going to get that from?
But we remember that first order kinetics has a constant half-life, and they give us the half-life.
Yeah, they give us the half-life, 10.9 hours, and there's an equation that relates half-life to the rate constant. T1/2 equals natural log of 2 over k.
Right.
And so I can use this to solve for k. Okay, so I put in the half-life, and I solve for k, and I find that, oh, the rate constant is 0.06359 hours to the minus 1. Those are the units. I don't have to change to minutes or seconds. I can just leave it like that. Now I can plug this in to my integrated rate equation. So negative 0.06359 hours to the minus 1 times 24 hours, that's my time point, plus natural log of my starting concentration.
Right, 1.5 mole.
So I get natural log of A at time t equals negative 1.1207. And how do I solve that?
Right, so to get rid of the natural log, you'll raise both sides to e.
Right. So I get at the end the concentration at time t is 0.326. Now I want to check, make sure that kind of makes sense.
Okay.
Right? Well, I know the half-life is 10 hours. Well, how many half-lives is 24?
24 hours is a little over 2 half-lives.
It's a little over 2 half-lives. So I expect the concentration to cut in half for the first one, then half again. So it should be a little less than a quarter of the original concentration. And if I take that and divide by 4, about 0.35.
Right.
So it is a little less than that. So that's a nice double check.
Right, which makes sense.
So I hope this helped in some integrated rate law problem solving, and see you in class.